there is a 25% of S character and 25% of P character in this hybrid orbitals. In the case of sp3 hybridized orbital, 20% of S character, 60% of P character and 20% of D characters. Boron trifluoride molecule, the boron atom has the atomic number 5 as a valence shell electronic configuration of 2, 3. Hello students, I am Ramya, lecturer in chemistry from Vidhyaashram, the Temple of Excellence, Mysuru. In the previous session, we were discussed about dipole moment, polar and non-polar molecule, valence bond theory, types of overlapping and nature of covalent bond, difference between sigma and pi bond, hybridization, types of hybridization, sp hybridization, sp2 hybridization. In this particular session, we are going to discuss about sp3 hybridization, sp3d hybridization, sp3d2 hybridization, postulates of VSE-PR theory, geometry of molecules in which central atom has a 1 or more lone pair electrons, prediction of shape of molecule by VSE-PR theory, molecular orbital theory, that is MOT, hydrogen bonding and its type. Types of hybridization, sp3 hybridization. In this type of hybridization, mixing of 1 s orbital and 3 p orbital, hybrid orbital of equivalent energies and shape. The 4 sp3 hybrid orbitals oriented in tetrahedral symmetry with a bond angle 109.5 degree with each other. There is a 25% of S character and 25% of P character in this hybrid orbitals. Example of molecule having sp3 hybridization. This is sp3 hybridized orbital. sp3 hybridization in methane. In the formation of methane molecule, the carbon atoms undergo sp3 hybridization. In the excited state, 4 electron, that is unpaired electron present in 2s orbital gets unpaired, occupies empty 2p orbital. The electronic configuration of carbon at ground state, 1s2, 2s2, 2p2. Carbon at excited state, 1s2, 2s1, 2p(x1), 2p(y1) and 2p(z1). The mixing of 1 s orbital and 3 p orbitals, the valence shell to form sp3 hybridized orbital of equivalent energies and shape. The 4 sp3 hybridized orbital formed directed towards corner of the tetrahedron. The angle between sp3 hybridized orbital is 109.5 degree. This is the tetrahedral structure of methane. sp3 hybridization in ethane molecules. Ethane molecule, both the carbon atom assume sp3 hybridized state. One of the 4 sp3 hybridized orbital of carbon atom overlap axially with similar orbital of their other atom of sp3 sigma bond, while other 3 hybrid orbitals of each carbon used to forming sp3 s sigma bond with the hydrogen. This is sp3 hybridized orbital with a carbon-carbon. This is sp3 and s hybridization with a carbon and hydrogen molecule. Here also it shows 109 degree 28 minutes bond angle. sp3d hybridization. Here the intermixing of atomic orbital of 1s orbital and 3p orbital and 1d orbital of almost equal energy intermixing to give sp3d hybridized orbital, which arranged in pyramidal bipyramidal geometry. Among them, 3 are arranged in trigonal planar and remaining 2 orbitals above and below the plane are at the right angle. That means it shows 90 degree bond angle. The equatorial hybrid consists the hybrid which are equivalent and directed towards corners of the equatorial triangle between them, that is 120 degree. Axial hybrid consists of orbitals which are equivalent and oriented perpendicular to the plane containing the equatorial hybrid, that is axial orbitals are axial polar hybrids. It shows 90 degree bond angle. Here in the case of sp3 hybridized orbital, 20% of S character, 60% of P character and 20% of D characters. Formation of phosphorus pentachloride, sp3d hybridization. At the ground state electronic configuration, that is 3s2 3p3. At the excited state electronic configuration, this is 3s1 3p3 and 3d1. PCl5 shows the sp3 dehybridized orbital, sp3d2 hybridized orbital, the intermixing of 1s orbital and 3p orbital and 2d orbitals of almost same energy giving 6 identical degenerate orbital, that is called sp3d2 hybridized orbital. These 6 sp3d2 hybridized orbital are arranged in octahedral symmetry by making 90 degree angles to each other. This arrangement can be visualized as 4 orbitals arranged in a square plane, and the remaining 2 are oriented above and below this plane perpendicularly. When all the 6 hybridized orbitals involved in the bond formation, the shape of the molecule is regular octahedral. The formation of sulfur hexafluoride at the ground state electronic configuration 3s2 3p4. At the excited state 3s1 3p3 and 3d2. This forms sp3d2 hybridization. Valence shell electron pair repulsion theory, that is VSEPR theory. The main postulates of VSEPR theory as follows. The shape of the molecule depends upon the number of valence electron or a valence shell electron pairs around the central metal atom or the central atom. The pair of electron valence shell, that is repel and one another electron clouds are negatively charged. These pairs of electrons tend to occupy such position in space that minimize the repulsion and thus maximize the distance between them. There are 2 more reasons structures can represent a molecule. The VSEPR theory model appreciable to any such structure. The repulsive interaction of electron pair decreases in the order lone pair and lone pair bond pair and bond pair and lone pair bond pair. The geometry of molecules in which central atom has no pair of electron. If the number of electron pair is 2, it shows linear structure, linear geometry. Example, beryllium dichloride, mercury dichloride, and the number of electron pairs 3, it shows 3 electron pairs, shows trigonal planar, and the number of electron pairs 4, it forms tetrahedral electron planar. And for the trigonal planar, the number of electrons 3, boron trifluoride is an example. For the 4 pair of electron, methane and ammonium is an example. The number of electron pair 5 shows 5 electron pair and shows trigonal bipyramidal, and the number of electron pair 6 shows octahedral geometry. For example, sulfur hexafluoride. For electron pair 5, example phosphorus pentachloride. Prediction of shape of the molecule by VSEPR theory, that is beryllium dichloride. Beryllium dichloride has a Lewis dot structure as shown in figure. The central beryllium has two bonded pair and its outer shell, the repulsion between these two pairs causes the molecule to be linear. This result molecule having linear geometry. The bond angle of this molecule is 180 degree. Boron trifluoride. Boron trifluoride molecule, the boron atom has the atomic number 5, has a valence shell electronic configuration of 2, 3. That is, boron has 3 valence shell electron. These electrons are shared mutually with a 3 fluorine atom, that is forms BF 3BF bond. In BF3, boron has no lone pair over it, hence BF3 has regular geometry. The shape, that is trigonal planar. The number of bond pairs 3, number of lone pairs 0 because there is no lone pair electrons, and total number of lone pair plus bond pair, that is 3, and shows 120 degree bond angle, exhibits or this shows trigonal planar shape. Methane molecule has a carbon atom has atomic number 6, has electronic configuration 2 and 4, that is carbon has valence shell electron, 4 valence shell electron. These electrons are shared mutually with the 4 hydrogen atoms to form 4 CH bond, and in CH4 has no lone pair electron over it, hence methane has a regular tetrahedral geometry. Here also there is no lone pair electron, the bond pair electron is 4, the total number of electron is 4, and the shape is regular tetrahedral shape. The shape of water molecule, here in the water molecule has 2 lone pair electron and 2 bond pair electron. It has bent V shape or inverted V shape. It shows a bond angle of 104.5 degree, and thus water molecule has bent structure. Shape of ammonia molecule. In ammonia molecule, the nitrogen atom shows 3 bond pair electron and 1 lone pair electron. The shape would be is distorted tetrahedral, but 1 lone pair electron, due to this repulsion, lone pair bond pair repulsion, the angle between lone pair and bond pair get decreases from 109 degree 28 minutes to 107 degree, and it shows pyramidal structure. Molecular orbital theory, that is MOT. MOT or theory was developed by F. Hunts and R.S. Mulliken in 1932. The salient feature of this theory, when atomic orbital combine linearly, they form molecular orbital. A molecular orbital is a regular region, a space where the probability of finding electron is maximum in a molecule. The atomic orbital, comparable energy and proper symmetry to combine to form molecular orbital. An atomic orbital is monocentric while molecular orbital is polycentric. The number of molecular orbital is formed is equal to the number of combining atomic orbitals. When 2 atomic orbitals combine, 2 molecular orbitals are formed. When one is known as bonding molecular orbital and another one is known as anti-bonding molecular orbital. The bonding molecular orbital has lower energy and hence greater stability than corresponding anti-bonding molecular orbital. The bonding molecular orbital are represented sigma and pi, while anti-bonding molecular orbital represent sigma star and pi star. Each molecular orbital can accommodate a maximum of 2 electrons with the opposite spin, and the molecular orbitals like atomic orbitals are filled accordance with the above principle, obeying the Pauli's exclusion principle and Hund's rule. Formation of molecular orbitals, that is linear combination of atomic orbitals, LCAO. Consider a hydrogen molecule consisting of two atoms A and B. Each hydrogen atom at the ground state electron is in 1s orbital. The atomic orbital of these atoms may be represented by the wave function psi A and psi B. The mathematically formation of molecular orbital may be described by the linear combination of atomic orbital can take by addition and by subtraction of wave function, that is psi A minus psi B. Therefore, the two molecular orbitals are sigma and sigma star. The sigma is the bonding molecular orbital and the sigma star is the anti-bonding molecular orbital. That is, sigma is psi A plus psi B and sigma star is psi A minus psi B. The molecular orbital of sigma by the addition of atomic orbital is called bonding molecular orbital, and while the molecular orbital, that is sigma star, formed by the subtraction of atomic orbital is the anti-bonding molecular orbital. This is sigma and this is sigma star. It's a addition of psi A and psi B, and sigma star is the subtraction of psi A and psi B. The qualitatively formation of atomic orbital can be understood in terms of constructive or destructive interference of the electron waves of the combining orbital. Bond order. Bond order is defined as the one half of the difference between the number of electrons present in the bonding and anti-bonding orbitals, that is Nb minus Na by 2. Bond order half, that is number of electron in bonding orbital to that of the number of electron of the anti-bonding orbitals. So, when we take the difference between these two, we will get the bond order. Bond length. The bond length decreases when the bond order increases. Magnetic nature. If all the molecular orbital in a molecule is doubly occupied or else a paired electron is present, we considered it has a diamagnetic. However, one or more molecular orbitals that are singly occupied or the presence of unpaired electron is to be considered as paramagnetic nature. For example, oxygen. Bonding in some homonuclear diatomic molecule, that is hydrogen molecule. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron, and this can combine all the two electrons in the hydrogen molecule which are present in sigma 1s molecular orbital. So, the electronic configuration of hydrogen molecule is 1s2 because each atom donates single electron to the sigma molecular orbital, and the bond order of H2 molecule can be calculated as given below, that is bond order half into Nb minus Na. Nb means number of electron in bonding orbital, that is 2, and Na means number of electron in anti-bonding orbital, that is 0. Hence, the bond order is 1. Hence, the hydrogen molecule in the form of H2. This means two hydrogen atoms are bonded to form diatomic molecule. Helium, the electronic configuration of helium is 1s2. Each helium atom donates a pair of electrons. In helium molecule, there would be 4 electrons. These electrons will be accommodated in sigma 1s or molecular orbital and sigma star 1s to antibonding molecular orbital. So, when we calculated the bond order, that is Nb minus Na divided by 2, and Nb and Na 2 minus 2 divided by 2, we get 0. Therefore, He2, that means helium is not a diatomic molecule because the bond order is 0. It does not exist. Helium exists in monoatomic molecule. It's a monoatomic. Lithium, the electronic configuration of lithium is 1s2, 2s1. There are 6 electrons in Li2. Electronic configuration of Li2 molecule. The above configuration is also written as Kk sigma 2s2, where Kk represent the closed shell, K shell structure. That means lithium molecule is stable and since has no unpaired electron, and it should be diamagnetic because when we calculated the bond order, the number of electron in bonding orbital minus number of electron in anti-bonding orbital. The number of electron in bonding orbital is 4. The number of electron in anti-bonding orbital is 2. And the bond order is 1. Carbon molecule. In the carbon molecule, we know that the electronic configuration 1s2, 2s2, 2p2, the 12 electron, that is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, 2pxy, 2px2 equals 2py2, and the bond order in C2 molecule is number of electron in bonding orbital, that is 8, 1, 2, 4, 6, 8, that is 8, and the number of electron in anti-bonding molecule, that is 4, and the bond order is 2. C2 should be diamagnetic because of the presence of paired electron, and C2 consists both pi bonds because of the presence of 4 electrons of 2 pi molecular orbitals. Most of the molecule is a double bonded and it is made up of sigma bond and pi bond. Oxygen molecule, the electronic configuration of oxygen atom is 1s2, 2s2, 2p4. Each oxygen atom has 8 electrons. Hence, O2 molecule, there are 6 electrons. The electronic configuration of O2 molecule therefore is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, that is equals to pi 2py2, pi star 2px1 and pi star 2py1. From the electronic configuration of O2 molecule, it's clear that 10 electron present in the bonding molecular orbital and 6 electron present in the anti-bonding molecular orbital. The bond order is 2 and the molecule should be paramagnetic. Why? Because there is an unpaired electron present in molecular orbital in the oxygen molecule. So, it is considered as paramagnetic in nature. Hydrogen bonding. Hydrogen bond can be defined as the attractive force which binds the hydrogen atom of one molecule with the electronegative atom of another molecule. This is considered as hydrogen bond. This is electropositive in nature and this oxygen shows electronegative in nature, and hydrogen bond is represented by dotted line while a solid line represents the covalent bond. Types of hydrogen bond. There are two types of hydrogen bond. One is intermolecular hydrogen bonding and another one is intramolecular hydrogen bonding. Intermolecular hydrogen bond, it is formed by the two different molecules of the same or different compounds. For example, hydrogen bond in case of hydrogen fluoride molecule, alcohol or water molecule, etc., that is forms intermolecular hydrogen bond, and intramolecular hydrogen bond, it is formed when hydrogen atom is in between the two highly electronegative, that is fluorine, oxygen or nitrogen atoms present within the same molecule. For example, in orthonitrophenol, the hydrogen bond is between the two oxygen atom. So, it is considered as intramolecular hydrogen bonding. Thank you.